Hello everyone, and welcome back. Last time we were looking at some applications of Newton's laws. We were looking at some different forces, and we were looking at static problems and dynamic problems. Today we're going to look at another kind of motion. We're going to be using Newton's laws again, but we're going to focus on just a particular kind of motion for today. This brings us to section number 5, which is entitled Dynamics of Uniform Circular Motion. So, first, what is uniform circular motion? Well, circular motion means something going around in a circle. So, let's imagine we have an object moving around in a circle, something like that, moving around this way. Uniform circular motion means that it's going at a uniform speed. So the uniform part of our circular motion means a uniform speed. In other words, a constant speed. So as this object goes around the circle, we're going to assume it's going at a constant speed. It's always moving at the same rate, so to speak. As an example, I have a very simple example here. So we could just imagine here's a ball going around in a circle. We can kind of assume that it's going around at a constant speed, and that is uniform circular motion. It could be going around this way. It could be going around this way. It doesn't really matter. It doesn't matter what the orientation is. Just assume it's moving around in a circle and moving at a uniform speed. Now, why are we looking at this? What's so important about a uniform circular motion? Well, there are many different objects that undergo uniform circular motion or almost uniform circular motion. Anytime you have something moving around in a circle, obviously, even if it's not moving at a uniform speed the entire way, for part of the motion, if it's going around at a relatively constant speed, it will approximate uniform circular motion. A car going around a curve as it's going down the road, if it turns one way or the other, during that curve, even if it's not going in a circle for the whole circle, okay, just as it's going around this curve, we can approximate that curve as part of a circle. And while it's undergoing the motion around that curve, we can approximate the motion as uniform circular motion. So there are actually many things that undergo uniform circular motion, at least approximately, or for part of their motion. Let's describe, let's choose some variables to describe our motion. First of all, let's imagine that the object is going in a circle of radius r, or part of its motion can be approximated by a circle of radius r. So we'll say the radius of the circle is r. We'll assume that it's moving at some speed v, which we are going to assume is uniform. The amount of time that it takes for one complete circle, even if it's not going around an entire circle, we can still define a period for the circular motion. So how much time would it take for this car, if we had a car going around here, how long would it take for the car to go around the entire circle if it were actually going around that whole circle? That amount of time we'll call the period. The period of the motion. So the period is the time for one revolution. One complete revolution. In other words, one complete circle. The symbol that we'll use for that is a capital letter T. Be very careful. Don't confuse this T with other things or other thing that we've used T for before, which is the tension in a string. So make sure that you know from context, anytime that you're using an equation with a T in it, make sure you know you're talking about the period. Capital T, that's for the time. So this is actually a time for one revolution, and the units of period are then seconds. So it's a time, how many seconds? A quantity that's related to the period that we will use relatively often, and we will see again later on, is called the frequency. While the period is the time for one revolution, the frequency is the number of revolutions per second. In other words, the period is the number of seconds per revolution. The frequency is the number of revolutions per second. So the frequency is the number of revolutions per second. The symbol that we'll use for frequency is a lowercase f. The relationship between the period and the frequency is a very simple one. The frequency is equal to 1 over the period. We can see that in, let's imagine we've got an object undergoing motion that takes 10 seconds to go all the way around. So let's say that t is 10 seconds. Well, how many revolutions per second does it make? If it takes 10 seconds to go around the circle, it's only going to make it around 1/10 of the way every second. So the frequency is 1/10 of a revolution per second. So the frequency is 0.1 revolutions per second. So we can see that f is 1 over the period, or the period is 1 over the frequency. The units that we'll use for frequency, revolutions per second, is called a hertz. H-E-R-T-Z. 1 hertz means a revolution per second or a cycle per second. We'll use frequency again later on when we have any kind of repetitive motion taking place. And the frequency is then how many of those repetitive motions, how many oscillations or how many revolutions per second do we have. The frequency tells us the number of times something happens, maybe I shouldn't say time, the number of occurrences that something happens per time interval. For example, I might say, I go shopping 2 times per week. 2 times per week, 2 shopping trips per week. That would be a frequency, a shopping frequency, for example. So frequency is very general. It means any kind of occurrence per time. All right, there we go. Excellent. How are these related? The radius, the frequency, the period, the velocity. Well, let's think about this for a second. How far does our object move in 1 revolution, in 1 circle? Well, it will go 1 circumference of the circle. So for 1 revolution, the distance traveled will be the circumference of the circle, which is 2 pi r. The amount of time that it takes for 1 revolution is the period. The speed then we can write as the distance per time, which is 2 pi r over the period. We can multiply by t, divide by v, and we can also write this as t is equal to 2 pi r over v. So there we go. We've got a relationship that then tells us how the radius of the motion, the speed of the motion, and the period of the motion are all related to each other. There we go. Now I want to ask you a question about this motion. Is this object undergoing uniform circular motion, is it accelerating? Is the object accelerating? I want you to think about that for a second. You might say, well, it's moving at a uniform speed, so no, it's not accelerating. But let's remember, how did we define acceleration? We first defined the average acceleration, and the average acceleration was delta v over delta t. But just a second, is that how we defined it? No, we didn't. Because remember, acceleration is what kind of a quantity? It is a vector quantity. So the average acceleration we defined as a vector equation. And then the instantaneous acceleration we thought of as the average acceleration, but measured over a very small time interval. In other words, a vanishingly small time interval. If we could imagine the limit where our time interval got so small, infinitesimally small, essentially if it went to 0, then that ratio, delta v over delta t, became the acceleration. And when we introduced this, I said, don't worry, we're never going to use this except for one time. Well, this is the time. We're going to apply this result to our uniform circular motion to try and figure out what's the acceleration. Now, why isn't the acceleration 0? Because the acceleration is not the rate of change of the speed, it's the rate of change of the velocity. And velocity is what kind of a quantity? It's a vector. Is the velocity changing? The speed is not changing, but the speed is only the magnitude of the velocity. Is the velocity changing? Yes, it is. What's changing? The direction of the velocity. When the object is over here, and let me just demonstrate this again. Let me give you an example of uniform circular motion, or approximately uniform circular motion. If we think about the motion of this ball, over here, when it passes this point, it's moving upwards. That's the direction of the velocity. When it's at this point over here, it's moving downward. The direction is different. When it's up here, it's moving this way. It's moving this way. When it's down here, it's moving this way. So the direction of the velocity is changing. If the direction is changing, the velocity is changing. And if the velocity is changing, there's an acceleration. Excellent. What is that acceleration? We know that our average acceleration we defined as delta v over delta t, as a vector equation. The average vector acceleration is delta v vector over delta t. And then the instantaneous acceleration is the limit for a very, very small time interval, delta t, as it goes to 0, of that average acceleration. To figure out what this acceleration is, we're going to do it in two parts. We want the vector acceleration, so we need to know what's the magnitude and what's the direction of that acceleration. We're going to do those two parts. We're going to find the direction first, then we'll figure out what the magnitude is. The direction of the acceleration will be the direction of the average acceleration for a very, very small time interval. And the direction of the average acceleration is the direction. Where does the direction come from for this vector? It comes from the vector part over here, delta v. So the direction of the acceleration will be the direction of delta v for a very, very small time interval. But what's delta v? Delta v is the change in the velocity. In other words, v final minus v initial. Let's imagine we're looking at our object as it is undergoing uniform circular motion. So here it is going around a circle. We're going to pick 2 points in the motion and find what delta v is for those 2 points. We'll pick one point over here where the object is moving straight up like this. And then we'll pick some slightly later time, maybe up here, where the object is moving up in this direction. And let's figure out what is delta v for those 2 points. Well, when the object is over at this point, and remember it's going around like this, so let me just emphasize, it's moving around the circle this way, going around and around. Here, our velocity looks like this, v initial, and I'll use these little arrows here for my velocity. So here's v initial. A short time later, when it's up here, it's moving in this direction, so this is v final. So we've got v final over here. What we want is then v final minus v initial. Let's remember, how do we subtract vectors? To subtract 2 vectors, a minus b, let's imagine we've got 2 vectors, a and b, and we want to subtract them, a minus b. We know that to subtract 2 vectors is the same as adding the negative of the second vector. So a minus b is the same as a plus negative b. And then, because we can switch the order when we're adding vectors, the vector x plus y is the same as y plus x, a plus negative b is the same as negative b plus a. So to subtract 2 vectors, we're going to figure out what is negative b plus a. We're adding those 2 things. So we need to figure out what negative b is. To subtract two vectors, A and B, the first thing we do is we put them tail to tail. So I'm going to take these two vectors, A and B, and I'm going to draw them tail to tail. I know that when we have talked about adding vectors, we always say we put them head to tail, head to tail. When we're subtracting vectors, we're going to do something a little bit different, and you'll see why. The first thing we'll do is we'll draw them tail to tail. I'm going to take A, and I'm going to redraw it down here, and I'm going to try and draw this in exactly the same direction as my original vector, A. So there's A. And then I'm going to bring down B, and B looks like that, approximately. Okay, so there are A and B, and I've drawn them tail to tail. But I don't want to add A and B, I want to add negative B to A. So we need to figure out what's negative B. What is the negative of a vector? The negative of a vector is a vector with the same magnitude as the original vector, but pointing in the opposite direction. So I can draw negative B just by changing the direction of B, and it is now negative B. I can now add negative B and A. What do we get when we add two vectors? Well, we have to put them head to tail. But I already have that now. The head of negative B is now at the tail of A. Because I switched the direction of B to negative B, rather than being tail to tail as A and B were, they are now head to tail because we're looking at negative B and A. To add these two together, I put them head to tail. The sum then goes from the tail of the first to the head of the second. So the sum then goes from the tail of the first to the head of the second. And that is negative B plus A, or A minus B. There we go. I'm going to redraw this and put it back in terms of B again. So I'm going to change this direction. And let's think about what we've done. To find A minus B, we draw the two vectors, A and B, tail to tail. So we put the tails together. A minus B then is a vector that points from the tip of B to the tip of A. In other words, from the tip of the negative vector to the tip of the positive vector. Let's keep that in mind. When we want to subtract vectors, we take the vectors and we put them tail to tail. The difference then is a vector which goes from the tip of one to the tip of the other, and it goes from the tip of the negative vector to the tip of the positive vector. So A minus B would go this way, B minus A would go that way. Obviously the opposite direction. Very good. Now what do we want? We want V final minus V initial. So how are we going to find what's that direction? Well, we'll draw them tail to tail. So I'll leave V initial there and I'll bring V final down over here. So I'll redraw V final and bring it down over here. So there's V final. V final minus V initial then is a vector which goes from the tip of the negative vector. The negative vector is V initial. So from the tip of the negative vector to the tip of the positive vector, which is V final. So it points over this way. So there is the vector delta V. Let me get rid of my vector V final over here. So there is delta V. It points that way. But let's remember, we want to find the direction of delta V for a very, very small time interval. So we need to make the time interval between these 2 points, the initial point and the final point, smaller and smaller. In other words, we need to bring this final point closer and closer and closer to our initial point. Well, what's going to happen in that case? As we bring this point down here, our V final is going to rotate around like this and get closer and closer to V initial. Let's think about what happens to this direction, delta final, as we move V final closer and closer to V initial. Well, here's V initial, and here's V final, and we're going to bring this down here, And as the time gets smaller and smaller and smaller, V final rotates closer and closer to V initial. So delta V goes from this direction initially that we've drawn, but as V initial rotates up this way, what happens to the direction of delta V? Let me erase this, and I think you'll see it if I kind of get rid of this extraneous stuff, and we'll take another look at it.